Welcome to those of you who are watching on YouTube. We're just going into one of these quizzes. Quickly, we'll get started. I hope most of you are watching on YouTube, given that there's only 3 students in attendance right now. Okay, let's just get cracking. Data structure in which the last item added is the first item removed. So this test is all on what we learned last week, guys. Last item added is the first item removed. Nice, I'm glad everyone got it. That's very good. Yeah, so last in, first out, right? Like a stack of pancakes. I guess I don't have to explain this. Welcome, Taddy. No problem. If you can still join the quiz. So you just visit, you can see the details at the top of my shared screen there. So menti.com 323047 is the password. You've missed the first question that everyone got right, so you're going to be 1,000 points down, but we can see it. It'll be impressive if you manage to catch up. Let me know when you join so that I can, and then I'll continue with the next question. Your laptop is slow. Okay, cool. Well, not cool, but I'll keep it in mind. My laptop is also quite slow, actually, but mine's very old. Yeah, so just let me know when you're in. Yo, having fast Wi-Fi is so nice. Do you have fiber, Krefle? Yo, you should. Do you have DSTV though? And Taddy, let me know when you're in, hey? Yeah, I convinced my parents or my grandmother to quit DSTV, cancel it, and switch to fiber. And it was the best decision ever. Yeah. Does your sister have a YouTube channel or something, Bryn? What do you mean uploads? Okay. Tadi, are you here? Cool. Let's continue. Oh, that's cool. I want to see what the next item out of my data structure will be, but not actually remove it. Which command should I use? Oh, wow, all of you already answered? Sheesh. I didn't even read the question yet. Okay, this one's going to be very close because it's whoever's answering fastest. But yeah, well done. I'm glad you guys managed to get that. Data structure in which the first item added is the first item removed. Cool. Seems like you guys really, ooh, someone said list. Interesting. So remember, a list, you can technically, oh wait, you guys don't even know what a list is yet. So I don't know how you answered this. But yeah, stack, queue, array. Stack is last in, first out. Array is instantaneous access anywhere in the object. And a queue is first in, first out. Exactly how they work in the real world. Oh, okay, yeah, cool. Yeah, I guess the rushing. Yeah, exactly. Which 2 commands add and remove items to/from a stack respectively? So how do we add and remove? Geesh, you guys are quick. Someone, okay, cool. I did put that one in to fool you. So it's note, it says remove items. And remember that peek does not remove. Okay. Cool, that's awesome, Taddy, that's good. So I think the next question is the last question. It's not timed. So yeah, but do be careful about how you type things and stuff. So yeah, but remember guys, peek will not remove the item. It will just show you the item. But I'm glad most of you guys got this one. So that's cool. On to the last one, I think. I think it's the last one. Yeah. This is a typing one. Using valid C# code, complete the following to remove an item from the queue called myQueue. So we have myQueue dot and then space for you to fill in. Notice that the semicolon is already there. Okay, the semicolon's already at the end of the line. So you don't have to add the semicolon yourself. You just have to complete that blank to remove an item from the queue. The first item, obviously, because that's how queues work. The first item that was added. Okay, someone typed in the whole thing, which, you know what, I should give you credit for that. Unfortunately, I didn't put the whole thing in. Technically, the people who wrote DQ are wrong, but in all the other schools, no one remembered to put the brackets. Whoever wrote this pink one, technically you're correct, but look where the fill in the blank is. myQueue dot, and then you have to fill in the blank. Okay. I will give this to you. So I don't know, add 1,000 to your score. But yeah, DQ. But you do have to put the brackets, guys, whoever said this one. And push is how we add to a stack. It is not how we remove from a queue. Okay. But yeah, close. Those typing questions, it's difficult to put all the possible answers. Okay, cool. Nice, everyone. Yo, Beyonce. Geesh, I didn't know she was so good at computer science. Glad that we have a celebrity tuning in. Yeah, I'm kidding. Wow, Tuddy, are you serious? Yeesh, that is intense. Okay. That's impossibly good. Nicely done. But no, all of you did well. It was fairly. Don't worry about it, Kreflo. Which one did you write for the last question, Kreflo? Did you write the push or the myQueue or what? It auto-filled my name. Yeah, it does that. It usually picks pop stars, which I think was a weird choice, but whatever. You have next week, it will be fine, man. I skipped it. I forgot the command. Oh, okay, cool. Fair enough. Okay, so without further ado, let's get right into the lecture. I'm glad the quiz didn't take up too much time this week, but I do think they're fun. I actually played through all the quizzes with my family last night. So they were doing them, but obviously they haven't done any of the course, so they were getting everything wrong, but it was still fun. Wait, let me just, yeah, okay, I guess that's okay. Cool. So last week we discussed queues, stacks, and arrays. And the last one we have to discuss is linked lists. And then we'll basically just have one more piece of, one more item to discuss in chapter 4. So that's great. With this, we're coming to the end. And this is the end of first year computer science at university, by the way, after today's lecture. Hopefully, if we can manage to get through everything. Cool. So arrays, remember we answered different questions about each of the data structures, how to create them, how to access them, how to manipulate them, what their internal representation is in the computer, like a mental image of it. We start with chapter 3. So, well, we might write a mock test. We'll write a mock test as well. But I think you guys will be pleasantly surprised by it. It seems like you guys are pretty on ball. So don't worry too much. And then we discussed when to use them. This is an important thing to remember, guys. So we use arrays when we want instantaneous access to all of the items. So if we're accessing the items in our data structure very frequently, then we're going to use an array. All right. We briefly discussed the internal representation of arrays. We're going to discuss it in more detail later before we get onto linked lists. We also discussed queues last week. So they are a FIFO structure, first in, first out. We add to a queue using the NQ. So we type the name of the queue .NQ. And we remove from the array using the DQ. So DQ. All right. Peek will just show us the first item in the array, but it will not remove it from the array. There's one more command that we'll discuss for this as well, but let's just move on to the next thing quick. Okay. We also have stacks. Okay, we briefly discussed stacks as well, or not briefly. We spent quite a lot of time on both of these data structures. Stacks, sort of the opposite of a queue, right? So queue is FIFO, first in, first out. Stack is LIFO, last in, first out. How do we add to a stack? We use the push command. We remove from the stack using the pop command, and we can view the top item on the stack using the peek command. There's one more command that we'll discuss again after we cover linked lists, okay? Cool. So before we move on to linked lists immediately, I briefly want to discuss why they exist, because without knowing the theory for why they exist, they'll be slightly more difficult to understand. So in order to understand why linked lists exist, we actually have to go back and think about arrays. So I've got an array at the top of the screen there. 5, 6, 3, 4, those are the items in our array of integers. Okay. We remember that an integer is 32 bits in C# on a 32-bit computer, so quite a few clarifications, but if you remember 32 bits, you're fine. So this array is holding 32, 64, 124 bits, 128 bits of information, right? 4 integers, because each integer is 32 bits, right? So that's not too bad to understand, I don't think. So 32 would take us to the end of this bit, another 32 would take us to the end of this bit, another 32 to the end of this bit, and another 32 to the end of this bit. If we think about the computer's internal representation of this, we've got at index 0, we would just say 0 times 32. And so we access the 0th bit of the array, and we get 5. So this is why we start counting at 0, guys. It's quite an interesting thing to understand because it makes it very easy to access each item instantaneously, right? So you tell the computer, I want to get to this array in position 2, right? How does it calculate that? It goes, okay, 2 times by 32, which is the size of an integer in bits. And then it goes, okay, that's 64. So it goes to 64 bits. And it can get there instantaneously. It instantaneously jumps to 64 bits in this array, and then it's got your item. It knows that the next 32 bits is what it's looking for. Okay, so quite clever. Cool, so that's the internal representation of the array. The big advantage is that allows us to instantaneously access every single item we have stored in memory, right? We can instantaneously access the 5, the 6, the 3, or the 4. Okay. Where does the disadvantage of an array come in? Let's say I wanted to add another item to this array. So I want another 4. So I want the array to be 5, 6, 3, 4, 4. So I want a 4 here. Remember that arrays are contiguous and homogeneous. Okay? So they have to be next to each other in memory and all of the same type. So I just want to add another 4, so that's fine. You would have to create a new array. Let's visualize why we have to create a new array. You can picture if I was trying to add another 4 here, it would add over here, right? That's the next open space I have in memory. You can pretend this is Google Chrome or Grand Theft Auto 5 or something that's open here in this red block. But the point is it's a piece of reserved memory, okay? That red there. So I want to add my 4 to the array. Like the next open place in memory would be over here. But how would I access that? Remember, in order to access the last item, I would tell the computer 4, and it would go 4 times 32. So it'll try to access here, which is not allowed. So in order to create this new array, we would have to find a new open place in memory that can hold 5 integers. So it would have to have 150 bits. And then copy everything across. We would have to copy these 4 items across and add the last item, right? You would have to create a new array and copy the old elements across just to resize the array to hold 5 integers. You can see that's a massive disadvantage, right? It's also a fixed size regardless of what we use, but that's less important. Let's just in terms of resizing the array, it's very expensive. So linked lists were created to solve this problem, all right? This is the problem that a linked list will solve. So that introduced linked lists. Linked lists are designed to make it very quick to insert a new item and remove items and all of this kind of thing. You can picture also to remove the 6 in order to make it 5, 3, 4, right? Instead of 5, 6, 3, 4, I want 5 and position 1 to be 3 and position 2 to be 4. In order to do that in an array, the computer has to delete the 6, copy the 3 back, and copy the 4 back. That's a lot of work. You can picture if we have 1,000,000 items, we'll have to copy 1,000,000 items backwards. It's hugely expensive and slow to resize an array. Okay, but linked lists solve this problem and they do it quite well. So again, we are going to start by answering all of those questions for linked lists. How do we create it? How do we add to it? How do we use it? And just discussing some of the theories of linked lists. The first thing we're going to think about is called a singularly linked list. And you'll see it's quite simple and it's quite intuitive how it solves this problem that we've been discussing. So we start by creating this. And we'll do it this way in RexTester. I'll go ahead and open up RexTester now. But that's how we'll create this. I want to just explain what this is referring to at the moment. So this we'll refer to as the head or the link to the head node or the pointer to the head node. Okay, just think of it like that for now. And you'll see as soon as we create our linked list, it's pointing at nothing. Okay, it's just pointing at nothing. All right. And a pointer, the pointer will be represented in my diagrams with an arrow that looks like this. Okay, that's the pointer. And this is the head pointer, the pointer to the head, whatever you want to call it, something like that. Okay, similar to when we were discussing queues, it's a similar idea, almost like a snake. And that is basically what we're going to do. We're going to build a snake through memory. Okay, so let's just start. I'm gonna head over to RexTester and just do it there. Make this full screen. And we're going to create a linked list of integers. You could create a linked list of strings or whatever you want. Okay, it works for anything, but I'm just going to make mine for integers. So how will that work? We type linked list. Remember, for creating stacks, we just said queue, or for creating queues and stacks, we would just say like queue, my queue equals new queue, something like that. Okay. For creating a stack, we would just say something like stack, my s equals new stack, something like that, right? Linked list is very similar. There's one slight change though. Okay, not too serious because it's in generic. This is how we'll create a stack. We'll say create a linked list. We say linked list. We put these two arrows here, so like a less than and greater than sign. And in it, you type the type of the linked list. So our linked list is going to hold ints. You could say it's holding strings or doubles or whatever you want. So that's just the type that the linked list will hold. So this is going to be a linked list holding integers. You give it the name as usual. Tari won today, so our linked list is going to be called Tari. And then we'll say new linked list. Okay. Again, you have to say int because that's what our linked list is holding, and then just normal brackets. So it's very similar to creating a queue and a stack. And by the way, if it's coming from generic, I'm just going to mention this briefly, you can specify the type for queues and stacks as well. But I wanted to show you that it's not necessary. That's why we did it the other way previously. Okay, that's why we used system.collections instead of generic previously. Okay. But don't worry, you don't have to think about that too much. Remember, the important thing to know about each one is how to add, how to remove, and the internal representation and when we use them. Okay, that's the important thing to get, guys. But anyway, let's focus on linked list. So that creates a linked list called Tari, all right? And internally, what the computer's got there is just this, okay? A head pointer to nothing, okay? A pointer to nothing. And all a pointer does is it points to a place in memory, okay? So this is pointing to nothing at the moment, but yeah, you can also call it a link. You can also call it a link. So get used to using both words because both will come up in MTA questions, okay? So the first thing we want to do is add to our linked list. So how we add to a linked list is we do this. Right? That's how we add to a linked list. We add this type of structure. This structure, what we just added to this linked list is called a node. Okay, it's called a node. The node has two parts to it. Okay, it has the value, which we can also call the data. Okay, it has the value that it's holding, which in this case is our integer 5. It also has another pointer. Okay, so each node will have the value that it is storing, the item that it is storing, the data that it is storing, and get used to using all of that terminology. And it also has a pointer to another place in memory, right? That's what pointers do. They point to a place in memory. And each node will also have a pointer. And initially, each pointer is just going to point to nothing. Okay, so what did we do here? We created a node. We gave it the item we wanted this node to store, and we gave it a pointer pointing at nothing. Okay. How we add this node is we say the name of the linked list dot add last, and then the item we want to add. So I'll go over and do that. So let me add 5 to our linked list. So it'll be exactly like this, right? So we'll say tuddy dot add last, and we give it the value that we want to add, 5. Okay. Cool. So that's that. We've now got we've now added the first item to the linked list. I'm going to go ahead and add the other items as well. So we'll have a 6. And how will we add each item? Remember, we add a node for each item. So to add the 6, we add another node, we give it the data, and we give it another pointer pointing at nothing. To add the 3, we add another node, we add the data, which is 3, and we add a pointer pointing to nothing. Okay. To add the 4, we do so again. All right. So this is how we build up a linked list. Okay. So that's the linked list that I'm going to build quickly, and you'll be able to see what's going on. So I'll say tuddy.addLast. Okay. We add 5, 6, 3, 4. Okay. So I'm going to add 5, 6, 3, and 4. Okay. So that's building up our linked list. So you would have to do this for every, yeah, exactly. Every single piece of data you add, you don't just add the data, you also add the pointer. Okay. There are constructors, Taddy, that can build up a linked list given an array. So you can give it a list of items and it'll build it up. But that kind of thing you can read about in documentation. I want to focus on the things you'll be tested on in the course, obviously. But yeah, you can read about all of that if you need to, or ask me about it outside of lecture time. But yeah, for now, this is the way I want you to think about adding. We add one item at a time. You can add in the center. You can see there's lots of different commands. If I say tuddy.a, you can see I can add after a certain node. I can add before a certain node. I can add the first item, or I can add the last item. So there are different ways of doing it. You see Rex Tester auto-completed a whole bunch. Is this like an array where it can only hold one type of data or multiple? Linked lists, as they are implemented in C# are homogeneous. So exactly like an array, they hold one item. And we specify its type over there. Okay, so this linked list will only hold integers. Okay. So yeah, that's correct. Cool. But now it's on to the cool thing. How do we work with linked lists? So Tadi, did that answer your question? Are you happy with that? Cool. Cool. So this is a singularly linked list. That's what we call it. A singularly linked list would look like this in memory, okay, or in the computer's internal representation. So why do we call it a singularly linked list? Because you can see it only goes one way, all right? So all the arrows point one way. So we could get from the head node to 6, from 6 to 3, from 3 to 4. But we can't go back from 4 to 3 or 3 to 6, okay? So this is just next, next, next. All right, so that's the first thing to note. There is the one that we actually have in Rex Tester is not a singularly linked list. It's a doubly linked list. But I just want you to familiarize yourself with the terminology, okay? But don't worry, it'll make sense when you see the alternative. Let's first just think about how we actually work with this, right? Because so now we know how to create to it. We create a linked list. We know how to add it. So could you call a credit card a linked list because you swipe once here and then there, but it is saved. I suppose it's variably sized, I suppose you could say. I'm not sure I 100% understand what you're getting at. So could you... Yeah, let me think about it a little bit more, and we'll see where this is used in a bit. Okay. So let's first just see how to access items. Okay. Now, important thing to note about a linked list. Remember, arrays we use when we want instantaneous access because they are very fast, okay? We can instantaneously access every item in an array. If we're frequently accessing all the items in an array, then or if we're frequently accessing all the items in our data structure, we'll use an array because it gives us instantaneous access. A linked list allows us to insert and remove nodes very quickly. You can imagine, I'll just show you quickly. Let's say we wanted to remove the 3 here. It'll be very easy to remove the 3. All we do is we stop pointing at the 3 and we start pointing at the 4. And then the 3 is basically gone. Okay, so that's very quick. It's one change. I just have to make the pointer from 6 point to what 3 points at instead of pointing at 3. And instantaneously, I've removed 3. Okay. But let's focus on how to use it in Rex Tester because I think it'll make it make much more sense. As we discussed, each node in a singularly linked list has 2 items. It has the value and it has a pointer pointing to the next item. Okay. So let's focus on how to access 5. So I'm going to try to print out 5 from our linked list. Pretty simple process, but you'll see more complicated than on an array. So what I'll do is I'll say, obviously I'm going to print it out. So console.writeLine. I'm going to say tuddy.first.value. Tuddy.first.value. Okay. Tuddy.first.value. And if I print that out, you can see it gives me 5. Okay. So that's how you print out the value. What I want to show you is what tuddy.first is. So I'll say tuddy.first. I'm going to print out that. You can see it says this is a linked list node. Okay, it is a node. Remember, we've been discussing nodes this whole time. So the node has some data and it has a pointer. Okay. So you saw how to print out 5. You go to tuddy.thefirstNode.value and we get 5. What we're going to do in order to get the 6 is we'll say tuddy.first to get the first node. And then we're going to say .next. .next will jump to this node. Okay, it'll follow this pointer to this node. So we would say tuddy.first dot next dot value to get the 6. Okay, so let me just show you that in code, and hopefully it makes sense. So we'll say, I must just erase this quickly. So we say tidy dot first dot next dot value, and that will print out 6. Pretty good. In order to get the 3, we would have to say tidy dot first to get this node, dot next to jump to the 6, dot next again to jump to the 3, and then we would have to say dot value to get to the 3 inside this node. Okay. So that'll be dot next dot value. Okay. So tidy dot first, erase that again. So we'll say, yeah, it is, but you'll see why. Hopefully you can already intuit why this, it's almost the only way to get around this problem of having to have everything in contiguous memory. So it allows you to jump to items. Okay, there is a faster way to use this. Remember, you can automate a lot of this, but we're trying to understand the theory of this. So in order to access, so this, we're at node 5, the first node, when we say 5. To get to the second node, we say dot next. So that'll bring us to this node. To get to the node that holds 3, I have to say dot next again. And then you can see we can say dot value to get the 6. I mean the 3, sorry, to get the 3, because it's holding a 3. And you can imagine if I add another dot next, we'll get to 4. All right. Hopefully you can see how this does solve our problem of things being difficult to add, though, right? Because now they no longer have to be next to each other in memory, right? They can be anywhere. You can put the node anywhere in the computer's memory, and all you have to do is point to it. Okay. You just point to it, and then you'll get it, right? So in order to add another 4, I would just, instead of pointing to null, I'll point to another node that has, you know, the pointer and the data. Forgive my drawing here. And that'll just store another 4. And then this, we'll give it another pointer that just points to nothing. Okay. And this now just points here. Okay. So in order to add to it now is much easier. And you can see that we can add anywhere. Like if I wanted to add an item between the 6 and the 3, all I would have to do is put a node here. It'll have whatever value I want it to have. And we just, instead of pointing this here, we point it here. And then it just points to the 3. And bam, we've added another item. We didn't have to move any of the other items. We just found a place in memory and we store the node there. Okay, so it solves our problem. A little issue that a singly linked list has, so this is called a singularly linked list, because each item only has one list pointing to the next item, okay, the next node. Each node has one link pointing to the next node, or one pointer pointing to the next node. There is another way to do this, which is how C# does it, called a doubly linked list. A doubly linked list. And what a doubly linked list does is it doesn't just have a pointer pointing to the next node. Each node also stores a pointer pointing to the previous node. Okay, so this 4 will have another pointer, which I'll just draw on, that points to 3. Okay, and 3 will have another pointer that points to 6. Okay. And 6 will have a pointer that points to 5. Not too bad to understand, I don't think. It's just that each node has 2 pointers. Obviously, the first node, the previous pointer just points to nothing because there's nothing previously. When each node has 2 links like this, one going next and one going previous, we call it a doubly linked list. A doubly linked list, because each node has two links, okay, 2 pointers. So this is what C# has, and I'll show you that now in Rex Tester, and I'm sure it'll make sense. So currently we are accessing item 4 because we go .next, 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 okay? You can see if I went .next, we'll be at 3, right? So .next, .next, .value is 3. But I can also say .next, .previous, .value. So what will that do? I'll visualize it on our little linked list here. So we go head first, so Tadi first, brings us to this node, .next, .next, .previous, .value. So this will give us 6. All right. And you'll see that now. So you see it gives us 6. So you can jump forward and jump backwards if you have the pointer pointing to the previous node. Okay. Cool. So that's really linked lists. All right. As Tadi mentioned, it's pretty difficult to find out if something is in a linked list, but C# luckily provides a very easy command. Why do you want to use previous though? So remember, Tadi, let's say one common use for this, for example. So anything where we have variable sizes. So let's say there's a site where there's lots of pages, for example. Lots of pages that store text, okay? And we don't know where these pages need to be. They can be filled in anywhere, almost like a news site perhaps, or yeah, some scrollable thing. And let's say you want to scroll to the previous thing you saw. Remember that if you don't have the previous pointer, you can never go backwards. So picture it this way. Let's say this was a much longer list. Like let's say we had lots of items between the 6 and the 3. Okay. The 3 is the second last item, and the 6 is the second item. Oh, by the way, doubly linked lists also store a tail pointer. So a pointer to the last item in the list. So like the head, we also have the tail. Okay. I just trust me, that says tail. Okay. So we have a tail pointer as well. In order to get to 3 in a singularly linked list, you would have to say 5, .next, however many nexts there are between the 6 and the 3, and eventually you'll get to the 3, which is a lot of work. In the doubly linked list, you can just say you want to start at the last. So we start at 4 because we have a pointer to 4, and we just say .previous, and we've got to 3. Okay. So it makes it much faster to traverse the linked list. Okay. So having a previous is just a little extra piece of convenience. Okay. Does that make sense? So it just makes it much faster. So you don't have to say .next. You can sometimes, if it's closer to the end. Yeah, exactly. So you can start at the beginning or the end of the list, but also think about like if there's one of these swiping platform things, like these dating apps, you would go like .next, and let's say you want to see the previous thing, you swipe the other way and then it'll go previous. Remember though, you never have to like go more than one jump, right? In either direction, because like you'll go once. It doesn't really have to remember what the second last thing you saw was. You'll just swipe twice, right? So that's where it's useful if you're frequently accessing the next and the previous items, all right? And you need like quick access to next and previous. But yeah, there are other cases as well. Whenever you don't know how many things you're going to be adding to a data structure, we use a linked list because it allows us to instantaneously add and remove items. So if we're frequently adding and removing from a list, inserting and removing from a data structure, then we'll use a linked list. All right. Awesome. There is one more command. This command works with queues and stacks as well, by the way. But I'm just going to introduce it here, and it just makes it a little bit easier to see to check things out. So this command is called contains. Okay, so you give the name of your stack or your queue or your linked list. You say dot contains, and you just give it something that you're searching for, and it will search the entire linked list, the entire queue, or the entire stack. If the item you give it is in the queue or the list or the stack, it will return true. All right. So for example, I want you guys to tell me the answer. If I say tuddy.contains 2, what will this return? What will this print out? Okay, yeah, that was quick. I'm glad. It seems like you guys got it. So it'll say false. Why did it say false? Because tuddy very clearly does not contain a 2. Right? If I say dot contains 6, what will this print out? True, precisely. So you can see it goes true. Why? Because the second item is a 6. Okay. And this works with queues and stacks as well. So if you want to search, if you want to find out if an item exists in the data structure, we use the command contains. Okay. So particularly on stacks and queues, don't get confused between contains and peek. Okay. Peek will show you the next item that will come out of your data structure. Contains will search the entire data structure and tell you whether the item exists in the data structure. So that's a faster way of working with it. Okay. There are many other commands. You can see on linked lists, on queues, on stacks, on arrays, in C#. If you say dot, you can see it gives you so many commands. Look at how many recommendations there are here. Average, concat, count, distinct, equals. There are so many. We do not need to cover all of them, and we could never cover all of them, right? This is not a course about linked lists. Like you could have a whole course about just linked lists if you wanted to cover all of the things they can do. Okay. But as Creflo discovered with the .readLine command, when you're actually working with these things in the real world, you'll go to C#'s documentation about the linked list, and they'll have all the details about all of these commands there. Okay. These are just the commands we do need to know. Okay. So how to add to a linked list, whether a linked list contains something, and most importantly, when do we use a linked list? What problem does it solve? It allows us to insert and remove items from our data structure very quickly. It solves the problem of arrays. What is the problem with the linked lists? If we are frequently accessing all of the items in our linked list, if we are frequently accessing all of these items, and we're not frequently inserting and removing items, then we would rather use an array, because an array gives us instantaneous access to all of the items. The problem with an array is it's difficult to insert and delete. So that's the distinction you must understand. Okay. So it seems like you guys are pretty okay with this. So I'm happy about that. And now there would just be one more topic to cover in chapter 4. And that will be sorting. But we are in perfect time for a break, I think. We'll take a 10-minute break until 15:55. If you have any other questions, feel free to post them during the break, and we can go through them. Okay. But yeah, that's linked lists. This is a pretty advanced data structure. In first year computer science, you're asked to program this yourself as like one of your final projects. You make a class called linked list node with like a previous and next and value property, and you build up your own linked list structure. That's like an actual project that you'd be asked to do in first year comms. But understanding this data structure is a very good start. Especially since, yeah, some of you guys are very, very young to be learning some of this stuff. But yeah, next is sorting. When we come back from the break, we'll discuss sorting. Okay, feel free to post your questions in the chat if you have any. I will get to them. I'm just gonna go grab some water now quick, and then I'll be back. Cool. I see another person has joined us. That's great. Oh. So we're just on break until 5 to 4. And then we'll get started on BubbleSort sorting. Why do I use Linux? It's mostly to do with compatibility things with many things that I frequently use. But the main reason is the Linux terminal. This. It's way better than Windows's command line. Like you can do a lot of very cool things in it. Like it's actually a programming language in itself, basically, called Bash. Yeah, and it's for lots of things like, oh, I can give you one quite cool example. So there's a big server at Wits, like a server that you run a bunch of jobs on. So obviously a lot of the projects that you do and stuff, you can't run them. They use too much memory, or they need large graphics cards, like large, very expensive graphics cards. And I'm talking some of these graphics cards cost $15,000 each. So Wits has these massive servers, and you can very easily access them from here. So it's just as simple as saying, actually, I forgot. So I'll search through my history. So yeah, it's as simple as taking this command, you copy it. So I'm SSHing into, they call it SSHing, into that big server. I have like a password and an account, and now I'm on the server. So I'm currently working at Wits. This is all running at Wits, and you can check out what else is currently being running. So there's like a queue of everyone running their jobs. So you can see this guy's been running this job for 4 days and 1 hour on this big server. You can see all the jobs that are currently happening. So for this kind of thing, Linux is just by far the best. So you would, even if I was using Windows, I would have to get a Linux terminal or something. They call it PuTTY on Windows. But yeah, there's a bunch of things like this that Linux is just better for. So yeah, that's why. You can technically use Mac as well, but Mac is just expensive Linux. You'll also notice that if your computer feels slow or anything, it'd probably feel much smoother and faster if it was running Linux, because the file system is just more efficient and stuff. Okay, let's continue. So on to sorting. Firstly, no. We're ending at 4:30 because we started at 3, so 1.5 hours as usual. When have we ever been an hour, Krefler? So yeah, I'll just post in the chat. Yeah, okay, cool. So sorting, arranging systematically into groups or separating according to type. That's its formal definition that I just copied from Google. But in our case, it's more like arranging items into a predefined order, okay? Into any predefined order. So this can be alphabetically or anything like that. First question you might have, how the hell is this still section 3, right? We started by learning about the application lifecycle. Then we learned about data structures, and now we're learning about sorting. How are these topics related? So I would say it's not really the application lifecycle. I'm not sure why that's in the same section as data structures. It's confusing to me too, but it really makes sense that sorting and data structures are in the same section, okay? Because sorting is specifically to do with data, okay? We have a lot of data, like our array here, 5, 6, 3, 4. And to sort this array, and we can have another array here, Josh, Ali, Mayor, Dev. And to sort these arrays would be as simple as putting this one into some kind of numeric order, 3, 4, 5, 6, maybe 6, 5, 4, 3, right? Ascending or descending order. That would be sorting this array. You could also sort this array in alphabetical order, Ali, Dev, Josh, Mayor, or in reverse order or anything like that, right? That would be sorting. That's what we call sorting. So sorting and data structures are very closely related. All right, so that's why this is in section 3. Remember that the arrays themselves, the data structures that we are working with, can be gigantic, right? There could be 1 million numbers in this array. Huge arrays, right? Like if we're working at Google and sorting a bunch of login times, right? To see which accounts have been most frequently used or something like that. These arrays can be huge. We can have millions and millions of data points. So our approach to sorting needs to be automatic, fast, and memory efficient, right? Anyway, in order to discuss sorting, you see there's a lot of scope. We can sort according to alphabetical order, numeric order, any other order we wanted to define, right? Like the levels of different dragons in our computer game or whatever. Like this can get quite complicated. So we are going to make a simplification while discussing sorting, all right? If you think back, so in order to justify this little simplification that we're going to be making, if you think back to late in chapter 2, earlier in the course, we discussed a thing called iComparable. And what iComparable did was allowed us to create a way to compare any two objects any way we want, right? So we're going to assume that if there are two things, two objects, you'll be able to compare them. All right, we don't have to discuss that. I don't have to discuss with you guys how to define alphabetical order or whatever. Like we could figure that out if we wanted to. The main thing we're going to discuss, so just for simplicity, we're going to reduce our consideration of sorting to an array of numbers, okay, of integers specifically. So we are just going to focus on sorting an array of integers, okay, in ascending order. That's all we're thinking about. You can picture yourself how to adjust these algorithms to work for an array of strings or a linked list of strings or whatever you wanted, okay? We are solely considering an array of integers, all right? The algorithm that we're going to learn, BubbleSort, can adapt to different types, right? It can be used for strings or doubles or floats or whatever. And it can also be used on different data structures. But we are thinking about arrays of integers, all right? So it is more general than that, but we are just focusing in so that we can focus on the algorithm and the way the algorithm works. All right. So with that setup done, we are going to be learning about BubbleSort. This will be the first real algorithm that you guys have learned. A complex algorithm with lots of steps. This will be the first one that you're exposed to. So it might be a little bit hectic to visualize and stuff, but I've got animations and we'll spend the rest of the lecture on it. So don't worry too much, okay? Okay, BubbleSort, you'll find the stuff on page 76, 77 of your textbook, but the slides will be enough, but just for later reference if you wanna study through it yourself afterwards. Okay. So, in order to discuss our discussion of start our discussion of BubbleSort, we're gonna look at this array here. That's our array. And basically BubbleSort works on a series of comparisons and swaps. So we compare things and we see if we want to swap them. Okay, that's how it works. And we just compare two things. We compare any two integers together, and then we'll be able to sort the list. So this is how it works. We need to be able to compare two items in the array. Any two items in our array, if we're able to compare them, then we're able to sort the list using BubbleSort. Cool. So how does BubbleSort works? I've got an array here with 5 items, 8, 2, 4, 1, 3. I want to sort it in ascending order. Okay, so I want it to be 1, 2, 3, 4, 8. In that order, I want it to get to. How BubbleSort starts, we compare the first 2 items, 8 and 2. All right, you can see that 8 is larger than 2, right? And how would we check that in the computer? There's a bunch of ways we could check it, right? You could say, is the thing on the left greater than the thing on the right, right? You could ask, is that true? You could also ask, is this question, is the thing on the left less than or equal to the thing on the right? You can ask, is that question false? There's a bunch of ways you could phrase the question. But the point is, the thing on the left is larger than the thing on the right. And we would find out using an if statement, right? So we have an if statement. Is the thing on the left larger than the thing on the right? So it's just comparing these first 2 items. If the thing on the left is larger than the thing on the right, we're going to swap them. Okay? We are going to have to discuss this a little bit because swapping 2 items is probably more complicated than you think it is. Okay, so we're going to put BubbleSort aside for now, and we're going to think about how do we swap 2 places in memory, right? So we've got 8 somewhere in memory, and we've got 2 somewhere in memory, and we want to swap them so that 8 is where 2 was, and 2 is where 8 was. How do we actually do this swapping? Okay, it's probably more complicated than you would expect, as a lot of things are with computers. So in order to set this up, I'm going to create int x equals 8. Obviously, this is in an array in our case, but I'm just going to show you with 2 places in memory. So I've created a place in memory, x, that holds 8, and I've created a place in memory, y, that holds 2, all right? And by the end of this, I want to get to a point where x holds 2 and y holds 8. Okay, I'm going to print them out quickly, just setting up the example a little bit. I'm going to print out what the values of each thing are. Okay, I don't know if you guys remember this. It's an old way. We did discuss it once before, but all that's doing is, so this will print out x is currently 8. This is like a placeholder inside the string for this integer. So x is currently 8 and y is 2. Okay, that's all that's saying. So what I want to do is just, basically at the end, we want this instead to be x is 2 and y is 8. Okay, that's what we want to achieve. We want to swap these 2 items. Okay, how do we do this? Well, in the simplest sense, can you guys tell me how I would swap x's value for y's value? Can one of you tell me that in the chat? How would I do that? I want to make x 2 or whatever y is. I want to make x equal to whatever y is. How would I do this in C#? What line would I type? Oh, yeah. Okay. So this is just printing out afterwards. I want to make the actual variable that value, Taddy. I want to make the actual variable that value. So on this line here, I want to say x, and I want to make it, I want to change its value. So yeah, we would say x equals y, right? We discussed this a lot, right? All the equal sign will do is take the thing on the right and save it in the thing on the left, right? So it's going to take y, which is 2, and it'll save it in x. So now instead of being x8, y2, this will be x2, y2. Okay. But remember, we wanted y to become 8, right? So now how would I set y to 8? How do I set y's value to what x's value was? Yeah, remember, Teddy, we can't just say 8, though. This has to be general, right? If I made that 9, it must still work. So how do I set y to what x's value was? You would think, right? So what if I said y equals x? What would this do? You would see, Tari, you put a question mark there, which is good, because you can see that that won't work, right? This will still say x2, y2. So what's going on here? Think about how you as a human handle this problem, right? So what have we told the computer to do here? We said int x equals 8, int y equals 2. So the computer has 2 spots in memory, right? X and y, and it's made one of them 8 and one of them 2. We then say x equals y. So what does it do? It goes to the place in memory that is currently holding 8, and it makes it 2. So x is now 2, and y is still 2, right? We haven't changed y. Y is still 2. Then we say y equals x. But x is now 2, right? The computer overwrited that place in memory. Do you see that? So how do you guys, can anyone visualize for me? How would we get around this? We have 2 places in memory and we want to swap them. But you can see if I overwrite x, ooh, what happened there? Oh, that's so annoying. Oh, it removed all of my code there. Let me just rewrite it. Keep thinking about it though, guys. How would I swap their 2 values in this case? Because we have 2 places in memory. One of them is x, the other one's y, and we want to swap their values. But when I change x, I lose its value. How do we get around this? Well, remember, so Tari, think about what you remember what equals does, right? It takes the thing on the right and saves it in the thing on the left. It overwrites the thing in the left, right? So we're overwriting the original memory location. So how do we get around that? Can one of you think? You have to think a little bit outside the box, I think. How do we do this as a human? Because think about what the computer is doing here. When I say x equals y, I've now said x is equal to whatever's y's value is. X equals 2. Passing a reference, that's maybe interesting idea. That's maybe a little bit too out of the box. So what have we done here? When we said x equals y, we have forgotten what x's value was, right? X is now y. We just forgot y's previous value. It's out of memory. Okay. So this is an interesting little puzzle here. And I'll tell you how we solve it. The problem we are running into here is we have 2 places in memory. And as a human being even, when we want to swap 2 places in memory, you can't just use the 2 places. Okay, let me show you this. I'll draw it out to make it make even like more sense, perhaps. So we have 2 places in memory, okay, represented by these lines, right? They're not really lines or squiggles, okay? Represented by these squiggles, we have 2 places in memory. One of them is 8, the other is 2, okay? When we run this first line here, x equals y, when we run that line x equals y, what we are doing is we're coming, so this place in memory is x, and this place in memory is y. When we do this, what we are doing is removing the 8, and we are making it 2. So that's half the job done. X now is 2. The problem is y now needs to become 8, but we have forgotten 8. We've just forgotten it. It's no longer in memory. We haven't got 8 anywhere, right? So when we run this line y equals x, x is already 2. So what we need here, the way we get around this, we need a third place in memory. Okay, we need to remember what we are overwriting. So if I create a third place in memory, then this problem is now solved. Okay, because we would start with 8, 2. We go, all right, remember that what I am swapping out is 8. Okay, then I can say x equals y. So I overwrite this x with 2. Then I can go, all right, 2. I remember what 2 is supposed to be. 2 is supposed to be 8. That's now in my memory. So I overwrite the y with 8. And then I can go ahead and forget about 8. Right. So what the problem we were running into, in order to swap 2 places in memory, we actually need a third place in memory. You need to remember what you are swapping. You need to remember what you're overwriting. Okay. You can't, remember, you can only do it one step at a time. You can't instantly say x is y and y is x. You have to, there's an intermediate step. Yeah, exactly. We temporarily make another space in memory. Okay. And Bryn, temporarily is 100% the correct word to use, because when we do this, we call it a temporary variable, right? That's the name we give it. It's just a normal variable though, and you'll see how it works now. So in order to do this, I just create that third place in memory. We usually say int temp equals, temp obviously stands for temporary, okay? Int temp equals y, okay, or x, sorry. Int temp equals x. So I remember x, then I can say x equals y. So I overwrite x, and then I can say y equals temp. Okay. And that is how we swap 2 places in memory. Okay. And you'll see when I run this, at the end, x is equal to 2 and y is equal to 8. Whereas before, it was 8 and 2. Okay. So that's how we swap. All right. Pretty mind-blowing idea, I think. And you can see the nuance, right? When you're thinking for a computer, everything becomes just a little bit more complicated because you have to do it one step at a time. You can't just swap x with y and y with x, because it has to be you swap x with y and then you swap y with what x was before you swapped it. Okay. So hopefully we're comfortable with that idea. If you want to spend a little bit more time on it, it's not too bad though, right? We just needed this third place in memory. Okay, cool. So that's how we do that swap. All right. And as I said, yeah, probably a little bit more complicated than one would expect. Okay. So that allows us to sort the 2 and the 8, right? So initially it was 8, 2. We compared them. The thing on the left was larger than the thing on the right, so we swapped them. Okay, and we now know how we swap them. Okay, we have to store a temporary variable, and then we can swap. Okay, and in a way, we just repeat this process. Okay, so we'll move the blue line up. Okay, and we now compare 8 and 4. So it temporarily makes a third place in memory. So will it keep doing it until it can't? Well, whenever we swap two variables, Bryn, we'll create that temporary place in memory, okay, or use that temporary place in memory. You'll see how it works in the algorithm now as well, though. So, but yeah, exactly. Every time we do a swap, there must be this temporary place in memory that we create. But it's easy to create. It's just int temp equals x, or the thing on the left. Okay. So we would say, in order to do the swap here, we would say int temp equals the thing on the left, which is 8. Then we would say the 8 becomes the 2, and then we would say the 2 becomes the temp, and then they'd be swapped. And we would do the same here. So we compare 8 and 4. The thing on the left is larger than the thing on the right, so we have to swap them. And how do we swap them? We say temp is 4, 8 becomes 4, 4 becomes temp, and then they'll be swapped. Okay. And we keep doing that every time we swap. Okay. But afterwards, yeah, we can forget. After we've swapped, we only need the 2 spots. Okay. And then we go up again. So we compare 8 and 1. All right. The thing on the left is larger than the thing on the right. So we swap them. And we swap them in that same way that we just did, right? So temp becomes 1, 8 becomes 1. I mean, sorry, temp becomes the thing on the left, so 8. The thing on the left becomes the thing on the right, so 1. And then the thing on the right becomes temp. And we've got 1, 8. Okay. We move up again. Again, the thing on the left is larger than the thing on the right, so we swap them. How do we swap them? Well, we save the thing on the left into our temporary variable. The thing on the left becomes the thing on the right, so 3, and then the thing on the right becomes temp, and so they're swapped. All right, and that's how that is called a pass of BubbleSort. All right, so BubbleSort went all the way up the list. All right. Cool. So that was one part of BubbleSort. You see the list currently isn't sorted, right? We've now got 2, 4, 1, 3, and it must be 1, 2, 3, 4, 8, right? So we have to go again, but that was one pass. Yeah, you repeat this until it's sorted, and we will do that now. We will repeat it. So why is it called BubbleSort? So this is why it's called BubbleSort. Notice the 8 is in its correct space. The 8 is where it's supposed to be, right? The 8 is done. We've finished sorting 8. So what do I mean by that? When we finish sorting, we would expect, so the 8 started in the first place, right? When we finish sorting, we expect 8 to be in the last place because it's the largest number, right? What the BubbleSort does is at each pass, the largest number not in its correct place bubbles up to the top. Okay, so that's what we call it. It bubbles up. So 8 bubbled up to the top of the array. So the next thing that will happen is that 4 is going to bubble up to where 3 is currently. Okay, and you'll see on the next pass, just bear in mind what I've just told you. So the 4 is going to bubble up to where 3 currently is on the next pass, and you'll see that now. Okay. So let's do the next pass. We'll run over it every single step again. So we start. We compare the first 2 items. But 2 is less than 4. So we don't have to swap here. 2 is fine. 2 is less than 4. The thing on the left is smaller than the thing on the right, so we can leave it. And we immediately move on to the next comparison. 4 is larger than 1. The thing on the left is larger than the thing on the right, so we have to swap them. And we know how to swap them, right? The thing on the left gets saved into the temporary variable. We overwrite the thing on the left with the thing on the right, so with 1. And then we overwrite the thing on the right with the temporary variable, and they're swapped. Okay. We then move up again. 4, 3. So 4 is larger than 3, right? The thing on the left is larger than the thing on the right. So we have to swap them. And we know how to swap. Okay? And notice the 4 is now in its correct place, right? 4 is less than 8, so it's done. Okay, that's another pass. Notice the list is not sorted yet. So what will happen next? Well, you can see 3 is in its proper place, right? So the next thing that will happen is that 2 is going to bubble up to its proper place, right? And we can see on the next pass, we start here. 2 is larger than 1. The thing on the left is larger than the thing on the right. So we have to swap them. And again, the computer would keep going because obviously the computer can't yet know that the list is sorted, right? So it would keep going. But you can see that no more swaps would be made. Okay. So that's BubbleSort. It's not too bad, right? So it just works on a series of comparisons and swaps. So a comparison is where we compare the thing on the left to the thing on the right. 4 is greater than 3. And if that's true, we swap them. Okay. So there's a series of comparisons and swaps. And that's how BubbleSort will sort the list. All right. Okay, so that is BubbleSort. But obviously what we want to see is how do we actually program this? Okay. So let's go check this out in Rex Tester instead. Before that, I want to visualize, I want to describe what's happening here. So notice, Tari, when you asked, so would you do that until you have it sorted? When you asked that was quite a good time to ask it, okay? So what you noticed is that there is 2 levels of repetition happening, right? So we repeat the comparison, right? So we compare the first 2, then the next 2, and then the next 2, and then the next 2, right? So that's one repetition. We go over the array. But we also repeatedly go over the array, right? So we do this multiple times. So there is 2 levels of repetition here. We repeat over the array, and we repeat the repetition, if you like, okay? So what we have here is 2 loops. There is a loop inside a loop, okay? So there is a for loop inside a for loop, all right? So the first thing I want to mention, the outer repetition, okay? At each step, the reason it's called the bubble sort is because at each step, the largest number bubbles up to the top, right? 8 bubbled up, then 4 bubbled up, and then 3 was already in its correct place, but you could picture if 3 was in the wrong place, it would bubble up, and then 2 bubbles up, and then 1 bubbles up, right? 1 doesn't really need to bubble up because it's already will be in its correct place, but you can picture that each item in the array will bubble up, right? So we need to repeat once for each item in the array. We need to repeat the entire process of comparing and swapping for each item in the array. So that will define our outer for loop. So what I'm going to do here is create a quick method, all right? I'm going to do this I'll be pretty quick about it. So I'm going to create a method called BubbleSort. So I'll say public static. It is going to return an array of integers. So that's why the square brackets are there. And it's called BubbleSort, all right? BubbleSort. It also takes in an array of integers called R. I'm just going to call mine R, all right? So there we go. I've got a method here called BubbleSort. Okay. Outside of this method, I'm going to call it, obviously. So I'm going to say, I'll say int nums equals, I'll make it this exact one. So it was 82413. Okay, so 82413. 82413. Okay. And I'm going to call the bubble sort. So I'll say equals bubble sort on nums. Okay. So what am I doing? I'm saying nums equals bubble sort on nums, and bubble sort is just going to return the sorted array. Okay. At the end, obviously, we haven't programmed bubble sort yet. Okay. I'm just setting it up. And then just to make sure that it's working, I'm going to print out each of the numbers in order. Okay, so for int num in nums, I'm just going to create a little print statement here that'll print everything out. So this is just me setting up the programming. We haven't started programming bubble sort yet. Okay, this is just a nice little way to visualize what's going on. Cool. So you see that just prints out 82413 for now, because we haven't sorted anything yet. We just give the bubble sort method nums, and it saves it in nums again, and we return just R. We haven't sorted R yet. So our goal here is to use bubble sort to sort R. I think the way I'll explain this is we'll program the inner loop first, and then we'll repeat, just so that you guys can really get it, all right? We might go a little bit over time. I hope you guys don't mind. So the inner loop, what I'm calling the inner loop, is these internal comparisons. So what do I mean by that? We compare each item, right? We need to make the 8 bubble up. So let's focus on doing that first. We're going to program this first pass where we compare the first two, we swap, we compare, we swap, we compare, we swap, we compare, we swap. Okay. What I want you guys to do, I'm going to run through this animation. I want you to count the number of times the blue line appears and then post in chat at the end. Okay. So we do one comparison. The blue line appears. We do another comparison. We do another comparison. We do another comparison. How many comparisons did we do? 4. 4. Precisely. We did 4 comparisons. Can someone tell me? Actually, yeah, I'll be very explicit about it. So how many items do we have in our array? 5. Exactly. Tell me, can any of you tell me, can you extrapolate? How many times, how many comparisons would we do if we had 1 extra item in our array? We would do 5 comparisons, right? If we had 6 items, we would do 5 comparisons. You can see that. What if we had 7 items in our array? How many comparisons would we do? 6, exactly. What if I had 100 items in my array? How many comparisons would I do? Okay, 99. So you guys are seeing the relationship between the length of the array and the number of comparisons I have to do. Okay. So we will have to do 1 minus the number of comparisons, the length of our array. 1 minus the length of our array, or you know what I mean. The length of our array minus 1. Okay. Cool. The next thing I wanted to discuss is what we're comparing. Okay. So at each step, I'll do the first one and you guys do the rest. Okay. So at this first step, I am comparing item 0 to item 1. Right?
Yeah.
You see that because we start counting at 0.
No, I'm good, thanks.
Oh, Bren, I can hear you, by the way. So we compare item 0 to item 1. So I want, no, it's no problem. It's no problem. It happens all the time. We always forget. And actually, I don't mind for your mic to be on. You can speak through the mic for this next bit. Okay, so at this first bit, I'm comparing item 0 to item 1. So I want you guys to type the index of the 2 items I am comparing at each step, exactly like I did there. Okay, so the blue line moves. Which 2 indexes am I comparing now? Exactly. We're now comparing index 1 to index 2, right? And now 2, 3. Precisely. We are now comparing index 2, which is 8, to index 3, which is 1, right? And now 3, 4. Exactly. Index 3 to index 4. Okay. So you guys also notice what's going on there. You're correct. There are 4 comparisons, and we compare 0 to 1, and then 1 to 2, and then 2 to 3, and then 3 to 4, right? So it's like a very clear pattern that's going on here, right? Cool. So let's see what that looks like in code. We're going to go over that first step. We're going to make it so that 8 bubbles up to the top. All right. Let's do it. So we say for. That's a normal for loop, right? Very simple structure. We are iterating. I'm going to call our iterator I, as we're used to. We always call our iterator I, right? So I'm going to say int I equals 0. Okay, int I equals 0. I am running while I is less than the length of our array. R dot length is how we get the length of an array. So R dot length is just the length of R, all right? And then I'm going to say -1. And you know why the -1 is there, right? Because we always do one less comparison than the length of our array. That's the only reason that -1 is there. So this is running from 0 to 1 minus the length of our array. Makes perfect sense, I hope. Okay. And then we're just counting up by 1 each time. Okay, I plus plus. Cool. So what structure am I going to use to compare the 2 items? What structure will I use to create this blue line here? What structure am I using? Yeah, exactly. Well, BubbleSort is automated. So we're writing up the algorithm now, Taddy. This animation that I'm showing you on the screen, this is BubbleSort and we're programming it. Okay. So what structure am I going to use to program this blue line that's going across here to do this comparison? What structure? How do I compare the thing on the left to the thing on the right? What structure am I using? What statement? I'll ask that. What statement am I using? How do I find out exactly? Okay, we're using an if statement. All right. So I'll say if, and it's just a normal if statement, just like that, right? Pretty simple. Nothing too bad. Okay. I need to check. What do I need to check? I need to check that the thing on the left, if the thing on the left is larger than the thing on the right, right? So at first it'll be, is the thing in position 0 larger than 1, right? And our array starts at 0. It then goes up by 1. So is 1 greater than 2, right? So I would be at 1 when we get here, okay? Then I is 2, and we're comparing with 3. And then I is 4, and we're comparing with 5, okay? So what am I going to say? I'm going to say if R, the array in position I, is greater than R in position, what position is this, guys? Where am I going to access this? Where am I accessing the array? How do I get that other number? So remember, R starts at 0. On the next time round, it's 1, and then it's 2, and then it's 3. And look at the comparisons you guys just typed above this, right? 0 was compared to 1. 1 was compared to 2. 2 was compared to 3. Make a dependence on I, Taddy. So I goes, look what the for loop does. I goes 0, 1, 2, 3, right? How do I get what I'm comparing it to? So when I is 0, what was I comparing to? Remember the comparisons. Okay, let's do this again. Okay, because I do want you guys to get it. Okay, so we'll go again. Yeah, exactly. Okay. Tariq, you're on point. But let's think about it again because I want everyone to get it. Okay. So when this blue line is 0, right, we're on the first iteration of our for loop. So I is 0. We are comparing 0 to what? Item 0 to item 1. Okay. Second iteration of our for loop. The blue line moves up. We are comparing item 1, 8, to item 2, right? I is 1. Right? Then we are comparing item 2 to item 3, right? I is 2, so 3 is 2 plus 1, right? Then we're comparing item 3 to item 4, and 4 is just 3 plus 1. Okay, so Tariq, you are 100% correct on that. Nicely done. We say, is R in position I, that is the thing on the left, greater than the thing on the right? R I in position I plus 1, R in position I plus 1. Okay. If they are, then we want to swap them. Okay. How do we swap them? We say int temp equals the thing on the left, which is R in position I. Okay. We say we can then overwrite the thing on the left with the thing on the right. Okay, Ri equals Ri plus 1. Okay, and don't leave out semicolons. And then we say Ri plus 1, the thing on the right, equals our temporary variable. And so that's just doing the swap the same way we did it with X and Y previously, except now we're swapping the thing on the left with the thing on the right. All right. Cool. Now, when I run this, you see, guys, 8 has bubbled up to the top. So we've got 2, 4, 1, 3, 8. You see how 8 has bubbled up? So what have we programmed here? We have used this for loop to program this exact first part of the animation. So we compare the first two, then we compare the next, and swap, swap, swap. That is exactly what the computer just did. Okay. 4 comparisons and a few swaps. Okay. 4 swaps in this case because 8 was the first item. So it was always smaller than the thing on its right, right? We said we did a comparison and we swapped, we compared, we swapped, we compared, we swapped, we compared, we swapped. That's exactly what the computer just did. The next step is to make this repeat, right? We now need to repeat this. Okay. So how do we do that repetition? We have another for loop. Okay. So how will I do that? What I'm going to do, I'm going to tab all of this up just so that you can like visualize it. So we tab all of that up, and I'm going to say, I'm going to put this entire for loop in another for loop. Okay. So we say for, and you can see all of this code is going into the for loop. Okay. All right. So let me just do some backspacing, like remove these empty spaces. Yeah, exactly. It's almost like Inception. Okay. Have you guys watched Inception? Are you too young to have watched Inception? I don't know. You haven't. Okay. Well, okay, cool. So, cool. We just put the for loop inside a for loop to do the outer repetition, right? So we just need to repeat the exact same step we've done. We just need to repeat it once for everything in the array, right? So we say int j equals 0 while j is less than r dot length, j plus plus. Okay. And now you'll notice the array is sorted. 1, 2, 3, 4, 8. Now what's super cool about this? I can make this array as long as I want. I can put an 11 here. I can put a 0, 5, 7, another 4 if we want. We can make the array as long as we want, and you can see it'll always sort it. 0, 1, 2, 3, 4, 4, 5, 7, 8, 11. Okay. It is pretty hectic, and this is the first algorithm you guys have seen. But if you understand the animation, Tadi, I think with some revision or even just whatever questions you have, you will be able to understand it. If you understand the animation, then you understand the code. Okay. The only weird thing really is how we do this swap. Okay. Cool. Well, that is BubbleSort. What I'll send you guys, there is a nice YouTube video of some Hungarian traditional dances. So they dance in like a row, and they dance out BubbleSort. So I'll send you to that, guys. Send you that. It's one of those weird videos where I'm not sure why it exists, but it's pretty cool that it does. So I'll send that to you. BubbleSort as a Hungarian traditional dance. They also have other sorting algorithms. Okay. One important thing to take away. How does BubbleSort works? Yeah. So you will be able to play with it more, Krefler. I'll give you a recommendation now just before we stop. But let me just say one important thing. The most important thing you guys must know for now about BubbleSort is that it works on a series of comparisons and swaps. Okay. It works through comparisons and swaps. So if we were trying to measure how fast BubbleSort was working or how long the list was or something like that, we would count up the number of comparisons and swaps. Okay. Anyway, so yeah, just remember comparisons and swaps is how BubbleSort works. There is another sorting algorithm called quicksort. Okay, quicksort. Quicksort, as its name suggests, is quick. Okay, it is quicker than BubbleSort. It is also more complicated to understand. I'll create another animation that I'll show you guys next time. But what you must understand about quicksort is actually, yeah, we'll discuss it next week. Never mind for now. Okay, BubbleSort, comparisons and swaps. Cool. So we'll leave that there for now. What I want to show you next, just before we stop, sorry, I know we are going over time. This is pretty cool though, the sorting, I think. But I do just want to give you guys a recommendation. So there is a kata called sort numbers. Sort numbers. It is a 7Q kata. Okay, a 7Q kata. And all this kata is asking you to do is given an array of numbers, it gives you the array. It's called nums. So it's basically, we called it BubbleSort. They've got in a method called sort numbers, and they give you the array nums. Instead of our array was called R, their array is called nums. Okay, and if you manage to program BubbleSort in this, it will be correct. There is one extra hint that I'll give you, one tip. So before you start, you must write a quick if statement up here that says if nums is equal to null. So if they give you an empty list, you can see here they note it down. If they give you a null, you must just return an empty array. So if nums equals null, then you must just go return new int and then like an empty list. So just like open and close curly brackets like that. Okay. So you must type that at the beginning. And then here, just do BubbleSort on nums. Okay. You can do BubbleSort how I just showed you BubbleSort. There is a different version of BubbleSort. It's very similar, but there's a different version of BubbleSort in your book at the bottom of page 78. But the logic is very similar. I'll also send you the Hungarian traditional dancing video, and you can check out that one as well. But where I've put this comment here, BubbleSort on nums, if you put like some kind of BubbleSort or even another sorting algorithm there, then that will solve this kata, okay? And you just have to sort the list called nums. All right. So this is a good kata to do now if you guys want to learn about BubbleSort. All right. Cool. So I'll leave that there. 7Q kata called sort numbers is the one I recommend for this week and next. Okay. Anyway, I know I used a lot of your extra time. Sorry about that, but that is it for today. Okay. Thank you guys for coming. I'll post the lecture video as usual. Enjoy the rest of your weeks. Yeah, and that's true, Creflo. It is. There's a lot to play with in that code. You can improve it a lot and make it faster and stuff. It's interesting. Okay. Yeah. Cheers, everyone. See you guys next week. Enjoy your weeks. Cheers. Cheers.